On the night of the 10th of April 2019, Shepard Doleman and his collaborators at the Event Horizon Telescope project watched an image resolve on their screens, assembled from radio signals captured in Hawaii, Chile, Spain, Antarctica, and the South Pole. At first, it was just data. Then the noise aligned. A ring appeared uneven, glowing orange, wrapped around a perfectly dark center. This was M87, a black hole 55 million light-years away. For the first time in human history, gravity itself seemed to look back at us. No one rushed to equations. Silence arrived first. If this is the mouth of gravity, could it also be its womb? Because a black hole is where our most trusted laws stop speaking clearly. Space and time fall inward. Causes blur. The story appears to end. And yet, for decades, a small number of physicists have dared to ask a forbidden question. What if the collapse does not end in silence? What if, inside that darkness, a new expanding universe is born forever sealed from ours, carrying slightly altered laws of nature? This is not science fiction. It is a real hypothesis, argued seriously, debated fiercely, and tested wherever testing is still possible. In this journey, we will follow the most astonishing facts we have, from how stars are born, to how black holes might bounce, to a single neutron star whose mass may already be challenging the entire idea. Stay until the end, and you won't just hear speculation. You will arrive at the edge of a question humanity has never been able to answer clearly and finally understand what the possible answers truly are. If black holes tempt us with the thought of other universes, there is a quieter suspicion that starts even earlier. The universe that produced those black holes already looks strangely prepared for anything at all to exist. Imagine you come home late at night and step into the kitchen. The kettle is already on the stove. Water just below boiling. A mug waits on the counter. The lights are dimmed to a soft glow. A chair is pulled out from the table as if inviting you to sit. You were not expecting anyone. There is no note, no sound, just the quiet sense that the room has been arranged in advance for exactly what you are about to do. That is roughly how our universe can feel, once you start looking closely at its basic ingredients. The laws of physics, as far as we can see, are written in a small collection of numbers. The mass of the electron, the strength of gravity, the charge of the proton, the ratio between the strength of the electromagnetic force and the nuclear forces. They look like abstract parameters in equations, the kind of thing you might imagine could have been almost anything. Yet the moment you start to nudge them in your mind, you discover that they sit in an exquisitely narrow band where stars, galaxies, and chemistry are even possible. Change gravity a little, for instance. Not by some dramatic amount, just a modest tweak. If gravity were weaker, matter would struggle to gather. The tiny ripples left over from the early universe would not amplify enough. Gas would not clump, clouds would not collapse, stars would be rare or might not form at all. A universe of thin, almost uniform gas, quiet, simple, and sterile. Tilt gravity the other way and make it stronger. Then the universe is impatient. Clouds collapse too easily. Stars ignite, burn through their fuel, and die in violent collapse long before complex chemistry has time to play out on the surfaces of planets. Galaxies become crowded arenas of rapid birth and early death, with little room for long, stable eras where something like biology could tinker at its own pace. You can repeat this game with other constants. The masses of the quarks that build protons and neutrons. The small difference in mass between those two that allows hydrogen to be stable but also allows heavier elements to form in stars. The strength of electromagnetism that lets atoms hold together but does not glue electrons too tightly to move and bond. Each parameter lives in a range where, if you slide it too far, either atoms become impossible or only hydrogen exists, or nuclear reactions in stars simply do not work. There is a famous example involving the force that binds atomic nuclei together. If that force was slightly weaker, the fusion reactions in stars would struggle to build elements beyond helium. If it was slightly stronger, almost all hydrogen in the universe might have been burned into heavier elements very early, leaving no long-lived stars like our Sun and no easy fuel for water and organic chemistry later. The sweet spot is narrow, just right for a cosmos that makes both long-lived stars and rich chemistry. Even the energy of empty space itself, what we now call dark energy or the cosmological constant, seems oddly delicate. If it were much larger and positive, the universe would have flown apart too quickly for galaxies to condense at all. If it were large and negative, the entire cosmos could have recollapsed before stars had time to shine. Instead, we live in a universe that expanded fast enough to thin its initial fireball, but slowly enough to grow structure, and only later began to accelerate again. None of this, by itself, proves anything, but it leaves a taste. When you hear that a slight change in several different constants would give a universe with no complex structures, no stable stars, no heavy elements, or no time, it begins to feel less like stumbling into a random kitchen and more like walking into one that has been quietly prepared. This mood shift in physics did not happen overnight. For a long time, the constants of nature were just that, constants. Numbers you measured in the lab and then treated as fixed. The focus was on the laws themselves, the structures of relativity and quantum mechanics, not on why some mass or coupling had this specific value. But in the later decades of the last century, as cosmology grew into a precision science and particle physics became more intertwined with the early universe, people started to notice how many of these values are perched on cliffs. A small step one way or another, and the entire landscape of possible reality changes. Some physicists are comfortable leaving it there. The constants are what they are. Maybe there is a deep mathematical reason we have not yet found. Maybe there is not. But others feel an itch. When many different knobs all seem to sit near special positions where interesting things happen, it is hard not to wonder why. There is a simple, almost deflating answer. It goes under the name of the anthropic principle. In its modest form, it says something like this. Of course, we find ourselves in a universe where conditions allow for life and consciousness. If the constants had taken values that made life impossible, there would be nobody around to notice. Our observations are automatically biased. We only ever see universes that are friendly enough to produce observers. On a logical level, that statement is hard to argue with. It is a reminder about selection bias on a cosmic scale, but as an explanation, many people find it emotionally unsatisfying. It feels like shrugging at a prepared kitchen and saying, well, obviously it looks set up for tea, because otherwise you would not be here wanting tea. True, but not deeply illuminating. To make the anthropic idea feel more like physics, people often pair it with another concept, the multiverse. Instead of a single universe with one set of constants, imagine a vast collection of universes, each with different values for those basic numbers. Maybe they arise from different ways a deeper theory can crystallize. Maybe they are different regions of an eternally inflating space, each pocket cooling into its own version of physics. Whatever the mechanism, the picture is that there are countless cosmic realizations spread across a larger reality. In that setting, the anthropic principle becomes a statistical statement. If there are unimaginably many universes sprinkled with all possible combinations of constants, then it is not surprising that somewhere there exists a universe where the numbers happen to land in the narrow range that permits stars, chemistry, and life. We are simply in one of those rare pockets where the lottery ticket happened to be winning. It is like buying an enormous number of tickets in a lottery that is almost impossible to win. If only one person bought a single ticket and won, you might suspect something special. If an entire city bought tickets every day for years, and eventually someone won, you would not be shocked. The Multiverse story says, reality bought an outrageous number of tickets. Somewhere, a universe like ours was bound to show up. This way of thinking has real uses. In some speculative theories, the possible values of certain constants are set by the shape of extra dimensions or by fields that freeze into different values in different regions. You can then try to estimate how many of those regions would allow anything like our world to exist. The anthropic principle becomes a filter. Among all the universes that could exist, we are only ever going to perceive ones that satisfy fairly strict conditions. Still, for many physicists, the feeling persists that we got lucky in the multiverse is not the end of the story. It might very well be correct, but it does not yet feel like the kind of explanation physics usually strives for. It replaces why these numbers. With these numbers are rare, but somewhere they had to occur. It moves the mystery. It does not dissolve it. Part of the discomfort comes from how hard it is to test such ideas. If other universes are completely disconnected from ours, with no causal contact, then they behave more like philosophical scaffolding than like physical systems we can probe. The anthropic principle can then slide from a useful caution about bias into a catch-all excuse. Any strange feature might be dismissed as just what is needed for life, without a clear way to check. So the question deepens. Is there any way for these constants to be not merely given, but explained by some process? Not in the sense of a designer choosing them, and not in the sense of sheer brute luck, but through something like dynamics, a way in which universes, or the laws that govern them, could change, try out variations, and leave behind patterns. On a small scale, we already know of one framework that takes structures which look designed and shows how they can arise without any external planner. That framework is evolution by natural selection. On Earth, wings, eyes, and nervous systems give an uncanny impression of purpose. They solve problems. They seem aimed at flight, vision, survival. For centuries, that apparent design was used as an argument for a cosmic designer. Evolution changed that conversation. It showed that if you have entities that reproduce, if their offspring vary in heritable ways, and if some variants survive and reproduce better than others, then over long periods, you inevitably get structures that are well adapted to their environment. No plan required. The appearance of design comes from a blind process of variation and selection. The fine-tuned feel of our universe triggers a parallel temptation. When we see physical constants adjusted just enough to allow stars and chemistry, we reach for explanations that smell like intention or luck. Either someone set the knobs, or we simply happen to be born in the rare region where they landed just so. But those are not the only logical possibilities. You can ask a different kind of question. Could universes themselves, in some generalized sense, participate in a process that echoes variation and selection? Could there be a cosmic mechanism by which new regions of space-time come into existence, perhaps with slightly altered values of the constants, and in which some sets of values are more likely to continue that process than others? This is where black holes re-enter the story. Because if reality ever had a way of making new universes, it would probably happen in the places where our current theories strain the most. Where matter collapses catastrophically, where space-time itself is forced into extreme configurations, where the very notion of an inside and an outside begins to blur. We are not there yet. For now, we are still standing in the kitchen, looking at the prepared mug and the waiting kettle, wondering whether this arrangement is a one-off fluke, a result of some larger crowd we cannot see, or the outcome of some quiet, ongoing process deeper in the house. In this light, the central tension becomes sharper. Either the constants of nature were simply set, once and for all, in a way we do not yet understand, and perhaps never will, or they have been shaped by some process, perhaps unfolding across regions or generations of universes. One smells of design or luck, the other smells, at least faintly, of evolution. We are not going to resolve that tension quickly, but we can follow where each option leads. We can ask what our universe would look like if it were simply a lucky draw from a vast ensemble, and what it would look like if it were instead one branch in a cosmic family tree shaped by reproduction and selection. For now, we sit with a simple, unsettling fact. We are born into a universe that behaves as if it wanted stars, heavy elements, and long stretches of calm for chemistry to wander. The open question, hanging quietly in the background, is whether that impression is like the apparent design of a bird's wing, an illusion produced by a deeper process, or whether it is a clue that reality itself may have a way of making, and remaking its own conditions. If the constants of nature feel like the quiet settings of the universe, black holes are the places where those settings are turned all the way up, until the dial snaps off and the markings on it no longer make sense. Long before anyone had words like space-time or event horizon, a country clergyman in England was already imagining something like them. In the year 1783, John Michell wrote about what he called dark stars. He pictured a star so massive and so compact that even light, which everyone assumed was made of tiny particles, would not be able to climb away from its surface. The escape speed at its surface would be greater than the speed of light itself. Nothing, not even a beam of starlight, could get out. It was an extraordinary idea. And then, for more than a century, it simply faded from view. Physics moved on. Light became a wave, then a quantum. Gravity stayed Newtonian. The thought of a star that trapped its own light drifted into the background like a dream you forget by noon. The story restarted in the early 20th century, when gravity itself was rewritten. In the year 1915, Albert Einstein presented the field equations of general relativity. They described gravity not as a force pulling on objects at a distance, but as the bending of space and time themselves by energy and mass. A year later, while serving on the Eastern Front during a brutal war, Karl Schwarzschild found the first exact solution to those equations, describing the field outside a spherically symmetric mass. What he had actually written down was, in modern language, the geometry of a black hole. Einstein himself did not like that conclusion. For a while, nobody did. These solutions seemed pathological, like mathematical monsters that nature would never actually realize. But the equations were patient. They sat there, quietly insisting that if you pack enough mass into a small enough region, space-time can curve so steeply inward that nothing can escape. Not light, not signals, not even the idea of escape itself. It helps to say this carefully. A black hole is not a thing in space, like a solid ball painted black. It is better thought of as a region of space-time, where the geometry has become so extreme that all possible paths point inward. Imagine a river of space flowing toward a waterfall. Far away, the current is gentle. You can paddle against it. Closer in, the flow strengthens until there is a point where even a boat moving at the absolute maximum speed allowed by nature cannot make headway. Cross that point, and you are swept over. In the language of general relativity, that boundary is called the event horizon. Outside the horizon, you can still, in principle, turn and leave. You can send signals, wave, shine a flashlight, broadcast a message. Inside, every path you can take, every line you might draw into your own future, ends deeper in. There is no path that goes back out across the horizon, not because some force is yanking you, but because the structure of space-time itself has tipped so far inward that outward no longer exists as an option. At the center, in the simplest classical picture, sits something even stranger, the singularity. In the equations, it appears as a point where curvature becomes infinite, where density becomes infinite, where familiar quantities blow up. But that is a sign, not of a physical spike we understand, but of the limits of the theory itself. When physicists say singularity here, what they often mean is, our best description stops being meaningful. The map goes blank. General relativity has carried us as far as it can, and then, at some finite proper time in the interior, it simply stops talking. For a while, this whole story lived more in mathematics and philosophy than in the sky. Then, the observations caught up. In the middle decades of the 20th century, astronomers found bright, flickering X-ray sources in binary star systems. One member of the pair was ordinary, the other was invisible, yet so massive and so compact that gas falling onto it heated to enormous temperatures and screamed in high-energy light. These X-ray binaries were some of the first strong candidates for stellar mass black holes. On larger scales, the centers of many galaxies revealed the signatures of something heavier still. Stars near the core of our own galaxy swing around an unseen mass in tight, fast orbits, much too rapid to be explained by any collection of normal stars. The only consistent picture is a supermassive black hole, millions of times the mass of the Sun, sitting in the dark and holding the inner galaxy in its gravitational grip. Then, in the second decade of the 21st century, the universe gave us two new kinds of evidence, almost back-to-back. A network of laser interferometers listened for tiny ripples in space-time itself and heard the shuddering signals of black holes spiraling together and merging. A global collaboration of radio telescopes spread across the Earth, combined their vision and produced an image of the shadow of the black hole in the galaxy, Messier 87, a dark circle carved out of a glowing ring of infalling matter. These are not just speculative solutions on chalkboards anymore. They shake detectors. They bend starlight. They cast visible shadows in radio images. If black holes were only about crushing matter and trapping light, they would already be strange enough. But they also do something subtle to time. Imagine an astronaut drifting toward the event horizon, wearing a suit with a blinking light. From their point of view, nothing dramatic happens as they float past the horizon. Their clock ticks at its usual rhythm. They can move, think, feel, for as long as the remaining journey toward the singularity lasts. From far away, you see something very different. The blinks of the astronaut's light grow slower and slower. Their radio messages are stretched out. Their frequencies shifted to lower and lower tones. As they approach the horizon, the signals you receive from them arrive ever more infrequently, ever more redshifted, until they fade into darkness. To your eyes, the astronaut never quite crosses. They appear to freeze, dim, and smear across the edge. Both descriptions are correct within their own frames. For the infalling traveler, crossing the horizon takes a finite amount of proper time. For the distant observer, the approach is an endless asymptote. Reality is not choosing one storyline over the other. It quietly contains both. Time near a black hole becomes something you can only describe relative to a perspective. Already, that feels less like simple physics and more like a lesson about how deeply viewpoint is baked into the structure of the universe. The story becomes even more delicate when we allow quantum mechanics to join the conversation. In the 1970s, Stephen Hawking considered quantum fields in the curved spacetime around a black hole. When you combine the uncertainty at the heart of quantum theory with the notion of an event horizon, something unexpected happens. The black hole is not perfectly black. It emits a faint spectrum of radiation, as if it had a temperature, very slowly, over a time enormously longer than the current age of the universe for most astrophysical black holes. It can, in principle, lose mass and evaporate away. This radiation is not just a technical detail. It suggests that the boundary of a black hole is not simply a one-way surface, but a stage where quantum effects become unavoidable. It raises puzzles about what happens to information that falls in, whether it is truly lost, or somehow encoded in the outgoing radiation, or stored in delicate structures we do not yet understand. It tells us, very clearly, that general relativity and quantum mechanics cannot both be left unmodified in this regime. They are arguing with each other at the edge of the horizon. So far, all of this concerns what an external observer can see. The orbits of stars, the dance of merging black holes, the glow of hot gas, the slow leak of Hawking radiation. The interior remains hidden. Light cannot bring us news from beyond the horizon. No probe can return. And yet, mathematically, the equations of general relativity can be extended past that surface. Inside, the radial coordinate that used to measure distance becomes more like a time coordinate. The direction you might have called inward turns into something like tomorrow. You cannot choose not to move toward the center any more than you can choose not to move into the future. It is a region where every world line, every possible path through space-time, ends at the singularity in a finite interval. There is no static hovering, no circular orbit, only an unavoidable slide. For an infalling observer, the interior is not an abstract diagram, but a lived, if brief, experience. Tides stretching you. Light from the outside sky warped into a thin ring above. The center of the black hole no longer a point in space, but an inevitable moment in time. Physicists, understandably, hesitate at the idea of an actual infinite density. Past experience with infinities in physics has taught a simple lesson. They usually mean the theory being used is incomplete. In the 19th century, blackbody radiation calculations ran into infinities until quantum ideas cut them off. In quantum field theory, naive calculations diverge until renormalization and deeper understanding tame them. So when general relativity predicts a singularity, many suspect that it is not telling us that nature truly contains an infinitely sharp point, but that new physics, some form of quantum gravity, must take over before that happens. One possibility, explored in various approaches, is that the collapse might not end in a singular crunch at all. Instead, the extreme densities and curvatures inside might trigger a bounce. The matter and geometry fall inward, compress, reach a maximum density permitted by quantum gravity, and then rebound into a new expanding region. From outside, the black hole looks ordinary. An event horizon, a dark shadow, a long, slow evaporation. From the inside, it could feel like the birth of a universe. This is still speculation, and honest voices in the field emphasize that we do not yet have a full theory that can describe such a process cleanly. But the motivation is simple. Singularities are the places where our current laws lose their grip. If there is anywhere in nature where new laws might naturally emerge, or where space-time might reorganize itself into a different phase, it is there. Long before these possibilities were written down in equations, storytellers had already sensed that black holes make good thresholds. In Stanley Kubrick's film about a mysterious monolith and a journey beyond the known, a lone astronaut falls into a luminous corridor, moving through visions and distortions that are never fully explained. In the more recent story about a dying Earth and a mission through a wormhole, a black hole called Gargantua looms as both danger and doorway. In both cases, the black hole is not just an end, it is a passage. Cinema went there first because, on some intuitive level, black holes feel like places where narrative itself should twist, where outside and inside, before and after, life and afterlife, might blur, where the known laws could become permeable. Now, physics is catching up in a more cautious way. We have solid evidence that black holes exist, that they merge, that they sit in the centers of galaxies and whisper in gravitational waves. We also have equally solid evidence that our current theories do not fully describe what happens in their depths. Somewhere between the steady pull of general relativity and the restless jitter of quantum mechanics, something new must be hiding. The quiet question that grows from this is simple. If a black hole is the place where our present laws fail, is it only a dead end? A court-ordered termination of the story? Or could it be, in some cases, the one place where reality does something more creative, turning collapse into a beginning, and giving birth to new regions of space-time that are forever out of our sight? To imagine that universes might change and give rise to new ones, it helps to look at somewhere much smaller, where we already know that blind processes can carve the illusion of intention. Start with something ordinary. A bird's wing catching the air over a city park. A human eye tracking a moving cloud. The branching veins of a leaf pressed flat in a book. Each of them gives off the same unsettling impression, as if someone, somewhere, wanted them to do what they do. A wing looks engineered for flight, feathers layered to manage airflow, bones hollowed, light but strong, muscles attached at just the right places. An eye looks composed for seeing, a clear cornea, a lens that can change shape, a sheet of light-sensitive cells at the back, a brain behind it that somehow turns signals into a world. Even a leaf speaks a kind of quiet engineering language, light captured. Water and minerals moved along branching pathways that look, to a human mind, a little like wiring. For a long time, the most natural move was to read intention into that complexity. If you find a watch on the ground, with gears and springs arranged so that it keeps time, you assume a watchmaker. If you find a wing that passes air in just the right way to lift a body into the sky, you assume something similar, a mind, a plan. Charles Darwin knew that instinct very well. He felt it in himself. He also knew that if he was right, if his idea about how species change over time was correct, then that instinct would have to be gently set aside. You can picture him in his house in the English countryside, walking slow circles in his study, or along the sanded path in his garden that he paced so often it had a name. Manuscript pages stacked on his desk, letters from other naturalists nearby. The weight of what he was about to say pressing on him. The heart of his idea was simple enough to fit on a scrap of paper. If you have a population of living things that reproduce, and if their offspring are not perfect copies but vary slightly, and if some of those variations help them survive and reproduce better in their environment, then, over many generations, the helpful variations will accumulate. The unhelpful ones will disappear. No direction needed. No aim. No guiding hand. Just copying, variation, and differential survival. From that sparse recipe, something rich emerges. Eyes that see, wings that fly, leaves that harvest sunlight. Not because the system is trying to make them, but because any lineage that stumbles into those useful forms tends to persist, while other lineages simply fade. Darwin delayed publishing this for years, partly because he kept checking details, collecting more cases, studying more barnacles and pigeons and orchids. Partly because he understood the emotional cost. He knew that what he was proposing would unsettle centuries of thinking about purpose and design in the living world. He was not just offering a theory. He was pulling away a familiar story about why things look the way they do. When his book finally appeared, it did not say that life was meaningless, or that beauty was an illusion. It said something subtler and, in some ways, more unsettling. That purpose-like structure can arise without any overall purpose. That you can get watches without a watchmaker, as long as you have a great many attempts, a mechanism that copies itself with occasional mistakes, and a world that quietly keeps score by life and death. A key point in this story is that evolution does not aim at anything in particular. It does not have humans as a goal. It does not seek beauty or intelligence or even stability. It only does one thing, over and over. It preserves whatever works well enough, here and now, in a given environment, to leave more copies behind. If a complicated eye helps, eyes spread. If a simple light-sensitive patch is good enough, the process may never go further. If a structure becomes too costly to maintain, it may wither. From the outside, looking only at the finished forms, we see intricate adaptation and feel a pull toward teleology, toward stories of intention. From the inside, at the level of process, there is only variation and selection. Design is replaced by a history of filters. Now, step back from Earth. Think again about the way our universe looks. The constants of physics sitting in special feeling ranges. The conditions of the early cosmos tuned just enough that structure could grow. Long-lived stars. Rich chemistry. Time for planets to cool. And for complex, fragile things to assemble. Standing in that cosmic kitchen, looking at the kettle and the waiting mug, we feel the old intuition again. It looks prepared. It looks like something wanted complexity here. It looks, at least, like a fortunate accident of outrageous proportions. The leap that a few physicists make begins with a simple question. If evolution could take a raw planet covered in random chemistry and, over billions of years, produce forests and cities without any global plan, could something similar operate at a larger scale? Could there be a process by which entire universes or regions of space-time with different physical constants arise, vary, and are filtered, such that certain kinds are more common than others? To make that question precise, you need to import the bare bones of Darwin's logic. For any evolutionary process, three things must be present. First, reproduction. There must be some way for entities to give rise to new entities of the same general kind. Second, variation. The new ones cannot be perfect copies. They differ, even slightly, in some properties that matter. Third, selection. The environment, broadly understood, must be such that some variants have more descendants than others. Over time, these fitter variants dominate. On Earth, the entities are organisms. The copying medium is DNA. The environment is everything, from climate to predators to available food. In a cosmological context, physicists who think this way ask, could universes be the entities? Could something like a black hole collapse act as a reproductive event? Could the offspring universe inherit physical laws similar to its parent, but with small changes in the constants? And could there be a sense in which some sets of constants lead to more children universes than others? It is a daring analogy, and it needs to be handled gently. No one is claiming that universes sit on some cosmic tree filling out genealogical charts. There is no intention here, no cosmic body learning to be better at making universes. The point is to see whether the same abstract pattern that dissolves the appearance of design in biology could also, in principle, address the appearance of design in cosmology. The idea that pushes this forward has a name: Cosmological Natural Selection. It was proposed in the closing decade of the 20th century by the theoretical physicist Smolin. He was thinking explicitly of Darwin. He was also thinking of fine-tuning. Why does our universe look so suspiciously ready for complex structure? Is it pure chance in a multiverse? Is it a brute fact? Or could there be a mechanism that prefers universes of this kind? In Smolin's sketch, black holes play the role of reproductive organs. When a massive star collapses and forms a black hole, or when matter falls into an existing one, the extreme densities and curvatures in the interior might, in a full theory of quantum gravity, lead not to a singularity but to a bounce. That bounce could give rise to a new, expanding region of space-time, causally disconnected from the parent universe. A baby universe, if you like. In such a scenario, the laws of physics in the child universe might be similar to those in the parent, but with slightly different values for the constants. Not wildly random each time, but gently mutated, the way genetic information is changed by small copying errors. Universes that happen to have constants that make black holes efficiently would then tend to produce more offspring. Universes that do not make many black holes would have few or no descendants. Over long stretches of this meta-time, the population of universes in the larger multiverse would become dominated by those whose constants make black holes readily. Some sets of parameters would be sterile, others would be fecund. The appearance of fine-tuning would then be reframed. Our universe would look arranged for stars and heavy elements, not because it was chosen for life, but because universes that make stars and heavy elements tend to be good at making black holes, and those universes are overrepresented among the existing ones. This is the core of cosmological natural selection. It does not say that life is the goal. It does not say that black holes are conscious, or that the multiverse is trying to improve itself. It simply borrows Darwin's structure and asks what happens if you let it operate on the grandest possible scale. There are many caveats. This is speculation layered on top of a theory of gravity we do not yet fully possess. The bounce inside a black hole is an idea, not a confirmed feature of nature. The inheritance of constants from parent to child universe and the way they might vary are not derived from a finished theory. All of that has to be kept in view, but the emotional motive is transparent. It is the same desire that drove Darwin to spend years studying barnacles and finches. To explain apparent design without invoking external intention or a shrug about sheer luck. To show that structures which look as if they were aimed at something can emerge from a process that has no aim. On Earth, that process took raw chemicals and carved out eyes that look back at the universe. In the cosmological story, if it holds any truth, a similar pattern might take a larger space of possible physical laws and preferentially fill it with universes that are especially good at forming stars, heavy elements, and black holes. No one knows yet whether that is how reality works. The idea may turn out to be wrong, or incomplete, or only partly relevant. But as a thought experiment, it opens a door. If evolution can turn a wet rock orbiting an ordinary star into forests, oceans, nervous systems, and cities, all without a blueprint, then it is natural to ask, Given enough room, enough variation, and enough time in some generalized sense, what could evolution do to an entire multiverse? To let that question breathe, you follow it back to the places where new universes, if they exist at all, would most likely be made. The collapsed hearts of stars. So here is the bold version, said plainly. What if every black hole triggers a new Big Bang on the inside? If that sounds like something from late-night science fiction, you are not alone. Many physicists feel that way the first time they hear it. And yet, this is not an idea scribbled on the back of a napkin after a movie. It has been written down, argued about, extended, and critiqued for decades. It sits at the edge, where general relativity, quantum theory, and cosmology all lean in and talk over one another. In the middle of the 20th century, a physicist named Bryce DeWitt was one of the first to take seriously the quantum nature of gravity itself. He worked on what came to be called quantum geometrodynamics, an attempt to quantize the very shape of space-time. In that context, he looked again at gravitational collapse. Classically, as far as Einstein's equations are concerned, a sufficiently massive star that runs out of fuel and cannot support its own weight simply collapses. The outer layers may explode as a supernova. The inner core falls inward, crosses its Schwarzschild radius, forms a black hole, and keeps collapsing until, in the math, it hits a singularity. DeWitt wondered if that was really the end of the story. Quantum physics has a way of softening classical catastrophes. Where classical particles might slam into a wall, quantum wave functions spread and interfere. Where classical energy can plummet without bound, quantum systems often hit ground states. Perhaps, he and others thought, something similar happens to space-time in the extreme interior of a black hole. The picture that emerged in sketches and simple models was that the collapse might not march smoothly into an infinite density. Instead, as the curvature and density approach some critical scale, quantum gravitational effects could become overwhelmingly important. They might halt the collapse, store the energy, and then drive a rebound, a bounce. On our side of the event horizon, nothing obvious would change. The black hole would still be there, swallowing anything that comes too close, warping orbits, casting its shadow against glowing gas. Hawking radiation, if you wait long enough, would still leak away its mass. From the outside, the object is just a black hole, governed by mass, spin, and charge. But behind the horizon, in this speculative picture, the bounce could open into a new region of space-time that expands. To an observer in that newborn region, it would look like a Big Bang, hot, dense, rapidly inflating, and cooling. They would see their own cosmic microwave background, their own galaxies forming, their own history unfolding, without any knowledge that their entire universe emerged from the interior of a collapsed star in some parent cosmos. No signal can travel from inside their region to ours. The event horizon blocks any such communication. No signal can travel from our side into their early universe either, because their time direction points away from the pinch where the two regions join. They are causally sealed off from us, and we are sealed off from them. From our perspective, every black hole is a mouth. From their perspective, every black hole is ancient myth, if they ever infer it at all. They live entirely inside the consequence of the bounce, with no window back to the parent. John Archibald Wheeler, a physicist with a taste for vivid phrases, liked to play with this kind of idea. He talked about space-time foam at tiny scales. He coined the term black hole. He liked to say that space tells matter how to move, and matter tells space how to curve. And he was one of the people who pushed the thought further. If black holes create new universes, perhaps each new universe is not an exact copy. In Wheeler's vision, the cosmos becomes a branching tree. Each time a black hole forms and bounces, a new branch sprouts. The laws of physics in these branches might be similar, but not identical. Fundamental constants might take on different values. The masses of particles, the strength of forces, the value of dark energy, the behavior of inflation in the early moments, all could, in principle, vary. Some branches of this tree would be barren. Their constants might not allow for long-lived structure at all. No stable atoms, no galaxies, no stars. Others might allow stars, but not many black holes. Others might be extremely efficient at forming black holes, but in ways that lead to very different kinds of matter. In more modern language, this plays well with certain versions of string theory. In those frameworks, the universe has more than 3 spatial dimensions. The extra ones are curled up in tiny shapes, often described with the language of Calabi-Yau manifolds or similar objects. The specific way those dimensions are compactified helps determine the low-energy physics we see. What particles exist, what their masses are, how strong each force is. In that landscape, different regions of spacetime could have different shapes for the extra dimensions, and therefore different effective laws. Near the extraordinary densities and energies inside a collapsing black hole, those shapes might be pushed over energy barriers into new configurations. When the bounce happens and a new region of spacetime inflates, it could settle into one of these alternative shapes. The child universe then has different constants from its parent, not because someone chose them, but because the underlying geometry shifted. You can think of it, roughly, as a cosmic phase transition, like water freezing into ice, but with geometry and field values instead of molecules. The parent universe is one phase. The child, forming on the far side of the black hole bounce, is another. So far, this gives you a wildly branching multiverse, but one that might be quite chaotic. Each new universe could differ dramatically. Many of them might be sterile. Most might have no particular preference for black holes. This is where Smolin's twist enters. He suggested, in the 1990s, that the changes in the constants from parent to child are not huge random jumps, but small shifts. Slight changes, the analog of genetic mutations rather than total rewrites. If that is the case, then the space of possible universes gets explored locally. Each child is similar to its parent, but not identical. And that means that if some sets of constant values happen, by chance, to be especially good at making black holes, then lineages of universes near those values will tend to produce more offspring. Universes with constants that are bad for black hole production will, effectively, end the line. Over many generations, the population of universes living on this branching tree will then be biased. It will be dominated by those whose constants sit near local peaks of black hole fertility. Just as, on Earth, environments select for organisms that are good at surviving and reproducing there, the larger environment of the multiverse will be filled mostly by those universes that are good at reproducing through gravitational collapse. The narrative version goes like this. Somewhere in a much larger space of possible laws, a few universes with random constants arise. Most of them do almost nothing. They flash, perhaps, and fade. A rare few have combinations of constants that allow for long-lived stars, clouds of gas, cooling, and collapse. In those universes, galaxies form. Massive stars live short, luminous lives and die in core collapse supernovae, leaving behind black holes. In the interior of each black hole, a bounce produces a new universe, whose constants differ only slightly from those of the parent. Some of those children will make more black holes than their parent did. Others will make fewer. The ones that make more will, by definition, have more descendants. That is all that selection means here. Over some long meta-time measured in generations of universes rather than in seconds, the distribution of universes becomes heavily weighted toward those that sit near parameters maximizing black hole formation. Seen through this lens, our own universe starts to look less like a miraculous outlier and more like one particularly successful branch on a tall family tree. It is not special because it produced life. It is special because it is good at forming stars and black holes. Life rides on that success, like moss growing in the cracks of a thriving city. There is a quiet emotional shift embedded here. In many discussions of fine-tuning, the constants are framed as if they were chosen for life. That invites images of purpose, or at least of narrative centered on us. In cosmological natural selection, life is not the goal. It appears as a side effect, a passenger. The universe is good at making black holes. The fact that the same conditions also favor heavy elements, complex chemistry, and biology is, in this story, a bonus, not a design criterion. This can be oddly relaxing. It takes some of the existential pressure off. We are not the main event, not the reason the constants are what they are. We are a local expression of a deeper reproductive logic, one that cares nothing about meaning. The universe is not for us, and yet here we are, thinking about it. It is important to say, slowly, that we do not have direct evidence that black holes actually do this. We have strong evidence that black holes exist, that they merge, that they may evaporate extremely slowly. We have good mathematical reasons to suspect that general relativity breaks down at singularities. We have hints from various approaches to quantum gravity that bounces and new regions of spacetime are possible. But a baby universe inside a black hole is, at this point, an inference built on layers of theory. The bounce itself is hypothetical. The causal disconnection between parent and child universes means no light or particle can carry news back from the inside. Any mutation of constants is something we can only infer by thinking about how extra dimensions and fields might behave under extreme conditions. All of this lives in the still uncharted territory of quantum gravity, where our equations are at best approximations. So why take it seriously at all? One answer is that it is a concrete what-if that can, at least in principle, be sharpened into predictions. Assume, for the sake of argument, that universes reproduce through black holes, that constants mutate slightly from parent to child, and that the distribution of universes is shaped by this process. Then ask, what should our universe look like, statistically, if that is true? You should expect, for instance, that the combination of constants we observe sits near a point that maximizes black hole production. Given all the messy astrophysics, if small changes in a parameter would increase the number of black holes significantly, then we would live in a universe that is surprisingly suboptimal in reproductive terms. That would be evidence against the idea. In later parts of this journey, we will see how that logic has been applied to real astrophysical questions, like the maximum mass of neutron stars. For now, it is enough to note the strategy. Treat cosmological natural selection not as revealed truth, but as a working hypothesis. A story you can press on in specific places to see where it resists and where it breaks. There is also an aesthetic reason some people find this picture compelling enough to explore. It ties together three otherwise separate mysteries: the fine-tuned look of the constants, the existence and ubiquity of black holes, and the deep unease physicists feel about singularities where theories fail. In this narrative, black holes are not just wastebaskets for collapsed matter. They are the engines of cosmic reproduction. Singularities are replaced by bounces that both cure the infinities and generate new expanses of spacetime. Fine-tuning is not a coincidence, but the outcome of selection in a population of universes shaped by those very bounces. It may turn out to be wrong. Nature is under no obligation to affirm our aesthetic preferences. But the coherence of the story makes it worth taking to the point where it has to face data. Seen this way, black holes change their role in our imagination. Once, they were regarded as cosmic tombstones, the dead ends of gravitational collapse, absolute failures of matter to resist its own weight. Now, under the light of these speculative ideas, they take on a new possible identity. They are still dangerous. Fall in, and you do not come back. They still warp time and stretch space and turn ordinary intuitions about inside and outside upside down. But they may also, quietly, be where reality does its most creative work. It is an unsettling thought. The darkest objects we know, the ones that swallow light and erase detailed information about what fell in, might also be the places where new physics emerges and new universes begin. The cemetery becomes a maternity ward. For us, stuck outside, they remain silhouettes on the sky, rings of hot gas and shadow, ripples in space-time, mathematical puzzles, philosophical provocations. For the larger story, if cosmological natural selection or anything like it is true, they are something even more intimate. They are the reproductive organs of the universe, grounds for awe, because of what they might be doing beyond our horizon, and grounds for skepticism, because for now, that possibility lives mostly in the quiet space between equations and imagination. If black holes really are part of a cosmic reproductive story, then the next question is almost domestic. What ingredients does that story actually use? And why do those ingredients feel so familiar inside our own bodies? Picture yourself inside a dark molecular cloud. No stars, no sharp shadows, just a dim smear of starlight from the rest of the galaxy, heavily muffled by tangled curtains of gas and dust. In visible light, this place would look like a black cutout against the background, a hole punched in the Milky Way. From the inside, it is more like a cold fog that never lifts. The gas here is mostly hydrogen, with some helium mixed in. It is spread out, but not evenly. There are regions a little denser, a little colder. Gravity is working, slowly, tugging every atom toward every other. The cloud wants to collapse, but to do so, it has to get rid of energy. Falling inward heats gas up, and hot gas pushes back. If it cannot cool, the collapse stalls. Temperature in such clouds can hover around a few tens of Kelvin above absolute zero. That sounds cold, and it is. But early in the universe, when there were only hydrogen and helium to work with, cooling was much less efficient. Those two simplest elements do not offer many ways to radiate away energy. Their molecules have limited ways to rotate and vibrate, limited channels to turn heat into light. In that bare, primordial chemistry, star formation is sluggish. Clouds must grow very massive before they can overcome their own thermal pressure. The result is that the first stars are thought to have been enormous, rare, and born only in special conditions. The cosmos, at that stage, is capable of making stars, but it does not yet do so with the easy abundance we see in modern galaxies. Something changed. Generations of stars lived and died. In their cores, hydrogen fused into helium, helium fused into carbon and oxygen, and so on up the periodic table. When some of those stars died in supernova explosions, they threw those heavier elements out into space, seeding their surroundings. The next round of clouds was no longer pure. Mixed in with the hydrogen and helium were traces of carbon, oxygen, nitrogen, silicon, iron. That contamination, from our point of view, is a gift. Those heavier atoms can lock together into more complex molecules. Many of those molecules can radiate away energy much more effectively than hydrogen or helium alone. They have rich rotational and vibrational modes. In a cold cloud, they become the tiny machines that allow it to cool. Among them is a quiet hero, carbon monoxide. Two atoms, carbon and oxygen, bound together in a simple linear molecule. In star-forming regions, carbon monoxide is one of the main coolants. It can be excited by collisions with hydrogen and then radiate in millimeter and submillimeter wavelengths, carrying energy away. Astronomers map it with radio telescopes to trace where dense molecular gas is hiding. Because where carbon monoxide glows, star formation is usually nearby. Alongside these molecules are dust grains. Each grain is a speck of silicate rock or carbonaceous material, or ice, perhaps a fraction of a micron across. Individually, they are insignificant. Together, they provide shade. They absorb and scatter starlight from outside the cloud, protecting its interior from heating. On their surfaces, atoms can meet and stick, forming molecules like molecular hydrogen, water, methanol. Dust is both shield and workshop. Put all this together, and the chain becomes clear. Heavy elements produced in earlier stars mix into the gas. Those elements form molecules like carbon monoxide that radiate efficiently, helping gas to cool as gravity squeezes it. Cooler gas collapses more easily. Dust grains amplify the effect by blocking external radiation and by catalyzing molecular chemistry. Efficient cooling means more collapse into more dense cores. Those cores become stars. Not just a few rare giants, but whole clusters. From small red dwarfs to massive blue stars that live fast and die young. The upper end of that mass distribution is where the seeds of black holes are planted. Very massive stars, once their nuclear fuel is exhausted, no longer have the pressure support to resist gravity. Their cores fall inward. Some leave behind neutron stars. The heaviest likely form black holes. So the conditions that make star formation abundant and varied also make stellar black holes abundant. A universe rich in carbon, oxygen, nitrogen, and dust is a universe that cools well, forms many stars, and regularly produces the core collapses that lead to black holes. If cosmological natural selection rewards universes that make many black holes, then it will indirectly reward universes that evolve toward such metal-rich, dust-rich conditions. Now turn the mirror. Those same elements and structures are exactly what life, at least as we know it, seems to adore. Carbon, with its ability to form 4 bonds and build long chains and rings, sits at the heart of organic chemistry. Oxygen, both in water and in more reactive forms, is central to metabolism on Earth. Nitrogen threads through amino acids and DNA. Phosphorus, sulfur, trace metals, energy, metabolism, and cellular machinery. Dust and rocks become planets, with solid surfaces where liquids can pool and complex chemistry can concentrate. The water in your cells was once part of icy mantles on dust grains. The carbon in your bones was built inside earlier stars and scattered by explosions. The iron in your blood was forged in the intense conditions of supernovae or neutron star mergers. The atoms that make up your body were, quite literally, participants in the same chain of events that makes black holes possible. So in the story we are tracing, there is a deep overlap between the recipe for black holes and the recipe for life. The universe that is good at making one is, as a consequence, good at making the other. Not because life is the target, but because both require environments rich in heavy elements, with long eras of star formation and complex chemistry. This is not an abstract claim. You can see its outlines in the sky. Look at images taken by the Hubble Space Telescope of the Eagle Nebula, where towering columns of dark gas are lit from the side by nearby stars. Those pillars of creation, as people like to call them, are not only photogenic, they are also nurseries. Inside those columns, shielded by dust, pockets of gas are collapsing into protostars. Jets of material shoot out from their poles. Disks of dust and gas spin around them, cooling, fragmenting, beginning the long process that may one day produce planets. Or look at the Carina Nebula, rendered by the James Webb Space Telescope in rich infrared colors. The supposedly solid wall of gas is in fact lace, thin and perforated. Hot young stars have carved cavities and blown bubbles. In the ridges, dense knots and filaments hide forming stars. Warm dust glows. Molecular hydrogen and carbon-bearing molecules trace shock fronts and interfaces. It is messy, turbulent, and beautiful. In both cases, you are seeing, in a single frame, several layers of the same story. The raw material for future stars and planets. The young stars themselves. Some of those stars will be massive enough to end as black holes. The same clouds that will eventually host habitable planets are also, in time, going to host gravitational collapses that tear holes in space-time. In a sense, every such nebula is a factory. It manufactures stars of various masses, which in turn will manufacture heavy elements and, eventually, black holes. It also manufactures the seeds of planetary systems, where water can collect, chemistry can explore, and something like biology can get a foothold. From the point of view of cosmological natural selection, universes that lean into this kind of environment have an advantage. If universes with certain constants evolve toward plentiful carbon monoxide, efficient dust shielding, and long-lived molecular clouds, they will produce more stars and more high-mass stars. Those, in turn, will die into more black holes. The reproductive success of such universes is tied to the richness of their interstellar chemistry. Life, in this narrative, is riding the same wave. It does not shape the laws, it benefits from them. When the conditions are right for black hole production, they are, almost automatically, right for long-lived stars with heavy element-rich planetary systems. Over cosmic time, those conditions give rise to rocky planets with thick atmospheres, oceans, continents, and the complicated surface environments where life, once it appears, can diversify. There is a kind of quiet comfort and quiet disquiet in this. Comfort, because it suggests that life is not a completely freak accident balancing on a knife edge for no reason. Disquiet, because the underlying driver, in this picture, is something utterly indifferent to life. The universe, if it has in fact drifted into a regime that is good for black holes, did so because that makes more universes, not because that makes poets. Still, for beings like us, the alignment matters. The carbon that stiffens your spine and holds your muscles together is the same carbon that helps molecular clouds cool to the point where they can form stars. The oxygen that fills your lungs is descended from the oxygen that makes water and carbon monoxide in interstellar space, shaping the thermal balance of clouds. The dust that once shadowed a protostar, allowing it to grow, is cousin to the dust that eventually built planets like Earth. When you look at a deep image of a star-forming region, full of glowing gas and dark lanes, you are seeing potential futures for both black holes and living worlds. Some of those bright, short-lived stars will collapse all the way into gravitational darkness. Some of the smaller, steadier stars may host worlds with seas, weather, seasons, and perhaps in time, consciousness. In the strict evolutionary version of this story, that is not an accident to be celebrated as destiny. It is a coincidence of interests. The same physical settings that maximize one kind of reproductive success, measured in black holes, also happen to open a wide space for complexity. Evolution, whether of organisms or of universes, does not care about meaning. It cares about persistence. And yet, meaning appears. A universe, fine-tuned for black holes by a blind cosmic filtering process, produces a galaxy, which produces a star, which produces a planet, which produces life, which produces a nervous system that can sit in the dark and wonder why carbon monoxide lines are bright in molecular clouds. It can write down equations about star formation, build telescopes, point them at Carina and the Eagle Nebula, and see, in those clouds, both cradle and grave. If the theory is even partly right, then deep in your own body there is a trace of that larger story. The carbon in your bones and in the heart of a collapsing star are part of the same strategy. A universe, without intention, learning how to make more of itself by discovering through countless blind trials that heavy elements, molecules, and dust are the way to open that path. Even if the universe really is learning, without intention, how to use carbon and dust to make more of itself, nature has a habit of keeping spare roots hidden in the margins. So far, the story has leaned on a simple picture. Stars form in cold clouds. The most massive live bright, brief lives, and die in gravitational collapse. Some leave behind black holes. If black holes make baby universes, then any cosmos that is good at making massive stars ends up good at reproducing. That is the channel Cosmological Natural Selection loves. Stellar birth, stellar death, collapse. But gravity does not only know how to work through stars, and quantum fields do not stop fluctuating just because the sky has gone dark. Once a universe contains dark energy, its long-term future, as far as our current equations say, becomes very simple in outline. Space keeps expanding. Galaxies drift farther apart. Stars exhaust their fuel. New star formation slows, then nearly stops. Planets cool. Black holes, over unimaginable stretches of time, radiate away their mass. The night grows larger and emptier. The technical term for the state the universe tends toward, if the dark energy is truly constant, is something like a de Sitter phase. An ever-expanding space-time with a fixed vacuum energy. No more bright galaxies. No more new stars. Just a thin wash of leftover particles and the relentless stretching of distance. In that kind of universe, nothing much seems to happen. Yet quantum mechanics says that even what we call empty space is not truly empty. Fields have ground states full of jitter. Virtual particles flicker in and out of existence. Most of the time, these fluctuations are tiny, leaving no lasting trace. But in an ever-expanding universe that lasts effectively forever, extremely rare events are not forbidden. They are merely waiting. This is where the cosmologist Alexander Vilenkin adds a twist. He pointed out that in such a vacuum, there is a non-zero probability for a fluctuation big enough to create a black hole out of nothing but the underlying quantum fields. It is an absurdly small probability. So small that in any fixed region, over any normal length of time, you could safely ignore it. But in a universe that goes on and on, with more and more volume coming into being as space expands, these vanishingly rare events can accumulate. Picture the universe not now, but after almost all the ordinary action is over, far beyond any age that we can relate to our current cosmic history. All the bright galaxies have faded. The last stars have burned or become cold remnants. Black holes, the ones made from stars and galactic centers, have shrunk through Hawking radiation until they too have gone. What remains is a cold, thin, dark expanse driven by dark energy. In that deep future, most of space is uneventful. Yet here and there, separated by distances larger than any present supercluster, a quantum fluctuation is just large enough to nudge space-time into forming a tiny black hole. No collapsing star, no dramatic supernova, just the vacuum itself, stirred by quantum uncertainty, birthing a lone black hole in the middle of nowhere. Wait long enough, and such vacuum-born black holes could, in principle, become more numerous than all the black holes that ever formed from stars. They are not confined to the limited period of cosmic history when stars are common. They can continue to appear, sporadically, for as long as the dark energy keeps the universe inflating. Now fold that back into the cosmological natural selection story. Up to now, we have imagined that the important black holes are the ones made by stellar collapse, because those are the ones we see and model. But if black holes of any origin can trigger baby universes, then stellar black holes are just one channel among several. The vacuum itself is another. From the point of view of pure reproductive success, the question shifts. Which universes produce the most black holes, counting all channels, over their entire lifetime? A universe with lots of star formation early on can make many black holes in that phase. A universe with a very large dark energy density might expand so fast and produce so much vacuum volume that even extremely rare fluctuations become frequent in the total tally. In that case, the best strategy for a universe that wants, in scare quotes, to have many children is not necessarily to maximize stars. It is to maximize the conditions under which vacuum fluctuations form black holes. That tends to favor a very large dark energy density, a cosmological constant big enough that the universe balloons rapidly, generating vast amounts of emptiness where rare fluctuations can happen. But that does not look like the universe we inhabit. Our dark energy density, while non-zero and influential, is tiny when measured against many natural scales one might write down. It is large enough to accelerate the expansion today, but small enough that galaxies could form comfortably for billions of years. There is no sign that we live in a cosmos that chose to blow itself apart as fast as possible to maximize vacuum volume. If the vacuum channel is the dominant way to make black holes that seed new universes, and if cosmological natural selection optimizes for total black hole count across all time, then the theory would seem to push us toward universes with much more dark energy than we measure. In other words, toward universes very unlike ours. This is the essence of Vilenkin's objection to cosmological natural selection. Taken seriously, it turns the apparent fine-tuning on its head. Instead of being surprised that the cosmological constant is small, one might say, if universes really do reproduce through black holes, we should be surprised that it is not huge. The proponent of cosmological natural selection, faced with this, has a few moves. One is to question whether our current physics applies cleanly to such absurdly late times and exotic fluctuations. Perhaps quantum gravity or some other aspect of a deeper theory suppresses or forbids these vacuum black holes in a way we do not yet see. Another is to suggest that only certain kinds of black holes count for reproduction. Perhaps those formed through gravitational collapse of matter rather than fluctuations of the vacuum. These are not arbitrary evasions. but they are also not settled answers. They live in the normal, messy zone of scientific debate, where people test the edges of a theory's assumptions and see how much it can be stretched without tearing. The very fact that the discussion gets this specific is a sign that the idea has moved from pure metaphor to something that at least aspires to be quantitative. Once you admit that there can be more than one way to make black holes, the picture becomes richer and more complicated. Stellar collapse is one channel. Vacuum fluctuations in a de Sitter phase are another. There is also the possibility of primordial black holes, formed very early in a universe's history from density fluctuations, before stars exist at all. Different kinds of universes might favor different channels. You can think of this in ecological terms. An animal exquisitely adapted to the deep ocean is not necessarily well suited to a desert. A creature that thrives in the canopy of a rainforest would fail on an ice sheet. Evolution produces local expertise. It tunes bodies to particular niches, not to all possible environments at once. Universes, in this speculative view, might be similar. One universe might be optimized to produce stellar black holes, with parameters that favor long-lived molecular clouds, a rich initial spectrum of density fluctuations, and a modest dark energy that allows structure to form before expansion dominates. Another might be optimized for primordial black holes, with conditions in the earliest instance that drive large density spikes. A third might be optimized for vacuum black holes, with a dark energy density high enough that de Sitter fluctuations dominate over all other channels. In that sense, there could be several distinct ecologies of universes in the larger multiverse. Each ecology has its own main reproductive strategy. Each is shaped by selection pressures appropriate to that strategy. Stellar ecologies produce galaxies and long eras of star formation. Primordial ecologies front-load their black holes near the beginning. Vacuum ecologies are barren, of ordinary structure, but rich in dark energy, and patient enough to let fluctuations do the work. If we live in a universe that sits in the stellar ecology, that would help make sense of why we see galaxies, carbon, and dust everywhere, and why our dark energy is small enough to permit all that to happen. It would align the cosmological natural selection story with our observations, at least for this niche. But the more we allow other ecologies into the story, the more we have to face the possibility that the theory might prefer universes where our kind of complexity never emerges. Universes where dark energy is so large that galaxies never form, but where the vacuum still manages, through rare quantum convulsions, to make black holes in monstrous numbers over ages we can barely describe. Or universes where primordial density spikes litter the early cosmos with black holes, but never leave enough gentle space for chemistry to take root. For someone looking out from inside a life-friendly universe, there is a temptation to elevate our niche, to say that the only universes that matter are those with stars and observers. But evolution, in its starkest form, does not privilege awareness. It privileges whatever reproduces. If vacuum black holes make more babies, then, from the point of view of cosmological natural selection, a cold, empty, high dark energy universe might be more successful than one that blooms with galaxies and life. That is part of what makes this line of thought so quietly unsettling. It separates our values from the underlying mechanics. A universe filled with rich structure and feeling may actually be mediocre at the only thing that matters for its long-term representation in the multiverse. Spawning new universes. The right response to this is not despair, but curiosity. Does our current understanding of quantum fields in curved spacetime really imply that vacuum black holes abound in the far future? Does quantum gravity change that conclusion? Are primordial black holes robust predictions in any early universe scenario, or only in special ones? Can we, from inside our one universe, ever gather enough indirect evidence to distinguish between these channels? As those questions are argued over, something healthy is happening. The beautiful, tidy story in which universes evolve neatly toward being star factories is meeting alternative possibilities. It is being forced to clarify its assumptions and to confront scenarios where its main mechanism is no longer dominant. That tension is not a flaw in the scientific sense. It is a feature, a theory that can be threatened by new lines of reasoning, by different uses of the same equations, by alternative channels that change its predictions, is a theory that can, at least in principle, be tested and, if necessary, discarded. Only ideas that are vulnerable in this way can eventually give us real understanding. If there really is a kind of blind learning going on, at the level of universes, then at some point you have to stop telling the story and ask the harder question beneath it. What, exactly, would we expect to see? In biology, the answer is familiar. Evolution by natural selection does not produce perfect creatures. It produces creatures that are good enough to survive and reproduce in the environments they happen to inhabit. Given enough time and stability, lineages tend to drift toward local peaks in the landscape of possibilities. Not the highest conceivable peak everywhere, but a nearby hilltop where small changes in any direction usually make things worse. You can see this in the details of anatomy. The structure of a bird's wing is not the absolute mathematically ideal airfoil. It is a workable solution patched onto a forelimb inherited from reptilian ancestors. The human eye has a blind spot and blood vessels that lie in front of the light-sensitive cells, complicating the optics. These quirks are not signs that evolution failed. They are signs that it works with what it has, following gradients of improved reproductive success, not abstract design criteria. Transfer that picture to cosmology. If universes reproduce through black holes, and if the values of fundamental constants change slightly from parent to child, then you have a very similar setup. A population of entities that reproduce, variation in inherited parameters, differential success measured in number of offspring universes. Over many generations, the expectation is not that universes land on some unique, perfect set of constants ordained by mathematics. The expectation is that they tend to cluster near combinations of constants that are good at making black holes, given the constraints. Change the constants a little in one direction, you get fewer black holes. Change them a little in another, you also get fewer. The point you are sitting near is then a local optimum in the space of possible laws. That is the central prediction of cosmological natural selection, stated as plainly as it can be. If this kind of evolution really happens, then the constants in our universe should not be random. They should not be merely any values compatible with life. They should lie in a region of parameter space where the production of black holes is close to maximal, at least for the dominant channel at the cosmic epoch we inhabit. Put more operationally, the combination of things that control star formation, stellar masses, and the threshold between different kinds of stellar deaths should be delicately balanced. The amplitude of primordial density fluctuations that seed galaxies, the efficiency of cooling in molecular clouds, the nuclear reaction rates that determine how stars burn their fuel, the masses of particles, like the up and down quarks, and the electron, that control the stability of nuclei, the strength of gravity and the strong nuclear force. All of these should conspire so that galaxies are common, massive stars are neither too rare nor too dominant, and a healthy fraction of those massive stars end their lives as core collapse events that leave black holes. Now, actually calculating how all of that works as you nudge the constants is extremely hard. Astrophysics is messy. Change gravity, and you change not only star formation, but the expansion history of the universe. Change the strength of the strong force, and you alter which nuclei are stable, how stars shine, and what elements are available for cooling. Shift the electron mass, and you change atomic structure and chemistry. It is not a simple, clean knob where you adjust one parameter in isolation and watch black hole numbers go up or down. Still, you can make progress in patches. People have asked questions like, if you increase the strength of gravity while keeping other things fixed, do you get more or fewer stellar mass black holes? If you broaden the spectrum of initial density fluctuations, do you encourage more primordial black holes at the cost of disrupting galaxy formation? If you make carbon or oxygen less tightly bound in nuclei, does star formation become more or less efficient? In many of these rough explorations, there are hints that our universe is indeed perched in narrow, viable ranges. The chemistry of cooling in star-forming clouds relies on specific molecules and dust physics that would fail if certain nuclear properties were markedly different. The delicate balance that allows stars to explode as supernovae rather than simply collapsing quietly depends on equations of state and reaction thresholds that live in slim bands. Even the long-term survival of hydrogen, the simplest and most abundant element, involves mass differences and interaction strengths that could easily have been otherwise. These observations by themselves do not prove anything about cosmic evolution. They do, however, line up with the idea that the universe's parameters are not sitting on a wide, flat plateau where many other values would work just as well. They seem to be leaning against the edges of possibility in several directions at once. The temptation, especially from a human point of view, is to read this as fine-tuning for life. The constants feel just right for complex chemistry and biology, but in the cosmological natural selection picture, that framing is backward. The primary optimization target is black hole production. Life comes along for the ride because the conditions that are good for making black holes also, incidentally, create long-lived stars and rich chemistry. So if we want to ask whether our universe is near an optimum, we cannot define optimality in terms of how comfortable it is for us. We have to define it in terms of how many black holes it can produce. That means, at least in principle, counting black holes under different hypothetical tweaks to the constants and seeing whether our actual combination is close to a maximum. You can feel, at this point, how the conversation is shifting. Until now, the idea of universes evolving through black holes has been mostly a narrative, a way to think about fine-tuning, a way to connect black hole physics to cosmology. But science has to go further. A good scientific hypothesis does not only organize what we already know, it sticks its neck out. It makes predictions that could turn out to be wrong. Cosmological natural selection does this in several ways. One is the general statement that small changes to fundamental parameters should usually decrease black hole numbers. Another is more specific. There ought to be particular physical thresholds, particular knobs in nature, where the number of black holes is very sensitive to the setting. In those places, if the theory is right, we should find our universe sitting near the value that maximizes black hole production. The nice thing about such knobs is that they are easier to test. You do not need to recompute the entire history of star formation for every imaginable change in every constant. You just have to identify a physical parameter where the difference between one value and another clearly changes, whether stars end as neutron stars or black holes, whether they explode and eject heavy elements or collapse directly, whether certain cooling channels are available or not. There is an art to finding these points. You want something that depends strongly on one underlying quantity and weakly on others, so that you can make a clean argument. You also want something that leaves an observational trace, a feature in the sky, a population of objects, a measured limit. Remarkably, there is at least one place where the cosmic evolution idea manages to do this. It lives in the narrow borderland between the heaviest neutron stars and the lightest black holes, where the properties of matter at nuclear densities and the mass of one particular quark species team up to decide the outcome of stellar death. That is where this story will go next. For now, the tension is enough. If universes do evolve, and if black hole production is their reproductive currency, then our universe should look, in certain respects, as if it has been nudged towards settings that crank that currency up. If, on the other hand, we can find a natural knob that clearly controls black hole numbers, and discover that we are sitting far from the value that would maximize them, then the idea of universes evolving through black holes will be in trouble. Not emotionally, not philosophically, but in the one way that matters for a scientific hypothesis. It will have failed a test it set for itself. If there is a knob in nature that controls how many black holes a universe makes, it is not written on some gigantic dial in the sky. It is written in the tiny, dense hearts of dying stars. When a very massive star reaches the end of its life, its core runs out of fuel. For millions or billions of years, fusion in the center has pushed outward, holding gravity at bay. When the fuel is gone, the balance fails. The outer layers collapse inward. A shockwave may throw them back out in a supernova. The core, suddenly unsupported, falls. If the core is not too heavy, it can be saved from becoming a black hole by a new kind of pressure. Electrons and protons are squeezed together into neutrons. The star's heart turns into a single vast atomic nucleus, an object only a few tens of kilometers across, yet more massive than the Sunday astronomers call this a neutron star. A teaspoon of neutron star matter would weigh as much as a mountain. Inside, neutrons are packed so tightly that quantum rules about indistinguishable particles become structural. The same principle that gives ordinary atoms their size now provides the last line of defense against gravity. The neutrons cannot all be in the same state. They push back in a collective, quantum way. That push is what holds the star up. But there is a limit. If the neutron star's mass is too large, even this quantum pressure cannot support it. The exact boundary, the line between stable neutron star and inevitable collapse into a black hole, depends on the microphysics of matter at densities far beyond anything we can reproduce on Earth. It is encoded in what physicists call the equation of state of ultra-dense matter. The relationship between pressure, density, and energy. When particles are jammed together, almost beyond imagination. Below some critical mass, the star can remain as a neutron star, slowly cooling, perhaps spinning and emitting radio pulses like a cosmic lighthouse. Above that mass, there is no equilibrium. The star must continue collapsing until a black hole forms. That critical mass is the transition point. It does not just label a star, it silently governs the census of black holes in the universe. Now, add one more ingredient from particle physics. Neutrons and protons are not fundamental. They are made of quarks bound together by the strong nuclear force. In ordinary matter, we mostly meet two flavors of quark, up and down. There is a third light flavor, called strange. At the densities inside a neutron star, it becomes energetically tempting for some of the up and down quark combinations to rearrange into configurations that include strange quarks. If enough strange quarks appear, the star may no longer be made mostly of ordinary neutrons. Instead, it becomes a different state of matter, hyperonic matter, or in more extreme scenarios, a soup of deconfined quarks, including a healthy share of strange. This tends to make the star denser for the same mass. Denser matter is less able to resist gravity. The equation of state softens, the maximum mass that can be supported before collapse drops. The mass of the strange quark, then, becomes a hidden parameter in this drama. If the strange quark is heavier, it is harder to make. Strange matter appears at higher densities, perhaps only in the very cores of the most massive neutron stars. The equation of state stays relatively stiff, and the maximum neutron star mass can be large. If the strange quark is lighter, strange matter appears more readily. The equation of state softens earlier. The maximum neutron star mass falls. More stars tip over the line into black holes instead of remaining as neutron stars. Here, cosmological natural selection finds its knob. In this picture, the mass of the strange quark is not just an abstract parameter in a quantum field theory. It is a dial that controls how many massive stars end their lives as black holes, rather than as long-lived neutron stars. Turn that dial one way, you get more black holes. Turn it the other way, you get fewer. If universes reproduce through black holes and inherit their constants with small mutations, then the logic of selection says, universes in which the strange quark mass is tuned so that many massive stars cross the threshold into black holes will leave more descendants. Universes in which the strange quark is so heavy that few collapsing cores become black holes will leave fewer. Over many generations, you would expect the distribution of universes to cluster near values of the strange quark mass that maximize black hole production, subject to other constraints. Detailed calculations within this framework suggest that, for a broad class of plausible equations of state, the black hole census is maximized when the maximum stable neutron star mass sits at around twice the mass of the Sunday. Lower than that, and too many stars collapse quietly, reducing the number of exploding supernovae that enrich space with heavy elements. Higher than that, and too many massive stellar cores linger as neutron stars instead of becoming black holes. Somewhere near that 2 solar mass line, the trade-off is best. Wrap that into a concrete prediction. If our universe is indeed the product of cosmological natural selection optimized for black hole production through stellar collapse, then we should not observe neutron stars with masses significantly above about twice the solar mass. The population of neutron stars should cut off sharply near that value. Any heavier stellar remnants formed in core collapse should almost all be black holes. For a long time, that was consistent with what we knew. Measuring the masses of neutron stars is hard. You need systems where their gravity reveals itself in orbital motion. Typically, binary systems, where the neutron star orbits another star, or better yet, another neutron star, in a configuration that allows precise timing. The first such measurements suggested masses modestly above the solar mass, with uncertainties large enough that a two-solar mass ceiling was entirely plausible. Then radio astronomers started to find heavier ones. By timing the pulses from spinning neutron stars very precisely and watching how their orbits were affected by general relativity, they could weigh these compact objects with surprising accuracy. One system revealed a neutron star somewhat heavier than twice the mass of the Sunday. Another pushed that limit still further, to a value around 2 and a bit times the solar mass, with quoted uncertainties that left little room below twice the solar mass. At first glance, that looks like trouble for the cosmic evolution story. If you have a neutron star of, say, 2 1/5 solar masses, rested securely against its own gravity, then the universe has apparently allowed a maximum neutron star mass higher than the putative optimum. There are stars that could have been black holes, but are not. From the reproductive point of view, that seems inefficient. You can feel the tension. On the one hand, this is exactly the kind of test that makes cosmological natural selection scientifically interesting. It took a messy, metaphoric idea about universes having offspring and distilled it down to a specific, falsifiable claim about an astrophysical quantity. The maximum mass of neutron stars should be near twice the mass of the Sunday. On the other hand, the data are hinting that the real universe may not be playing along. The situation is not yet clean enough for a simple verdict. Theoretical models of dense matter are notoriously uncertain. Quantum chromodynamics, the theory of quarks and gluons, is hard to solve at the densities relevant to neutron star cores. Different equations of state predict different mass limits, and the onset of strange matter or other exotic phases can happen in various ways. The observational measurements, too, come with error bars and rely on modeling of the binary systems and the neutron star's structure. So when you compare the optimal maximum mass of roughly 2 solar masses from cosmological natural selection arguments with observed neutron stars near or above that value, several possibilities remain open. Perhaps the apparent overshoot is within the combined theoretical and observational uncertainties. The true maximum mass might still be very close to twice the solar mass, with the heaviest measured neutron stars sitting just below the cliff, their masses slightly overestimated by current methods. As measurements improve and models of dense matter sharpen, the numbers could still converge on the predicted value. Perhaps the optimum derived within the theory was itself approximate. The calculations that produced it made assumptions about how often different mass stars form, about how changes in the strange quark mass ripple through nuclear physics and star formation, about which black holes count most for reproduction. A more refined treatment might shift the optimum upward a little, into better agreement with observed neutron star masses. Or perhaps this is exactly what it looks like, a test that the theory is failing. If future observations continue to find neutron stars significantly heavier than twice the solar mass, with solid, independent measurements, and if nuclear physics models continue to support those high maximum masses, then the core prediction of cosmological natural selection about this particular knob will be contradicted. Our universe will not look tuned to maximize black hole production via the strange quark. This is where the philosophy of science quietly enters the room. In a famous essay, Karl Popper argued that what distinguishes a scientific theory from a non-scientific one is not that it is true or currently accepted, but that it makes risky predictions that could, in principle, be proven wrong. A theory that can explain anything after the fact, regardless of what actually happens, has no teeth. A theory that says, in advance, Here is a number, and if nature does not agree, I am in trouble, is taking a risk. That risk is a mark of seriousness. By tying the life and death of universes to the mass of the strange quark and, via that, to the maximum mass of neutron stars, cosmological natural selection has done something brave. It has stuck its neck out. It has said, if I am right, neutron stars above roughly twice the solar mass should not exist. The fact that observations are pressing right on that boundary, and perhaps beyond it, is not a failure of the idea's scientific character. It is the very thing that gives it substance. Even if, in the end, the evidence turns against cosmological natural selection, this episode will have been valuable. It will have forced astrophysicists to improve their measurements of neutron star masses. It will have encouraged nuclear physicists to refine their models of dense matter. It will have given cosmologists a concrete example of how a speculative multiverse idea can be dragged, however reluctantly, into contact with data. For now, we are in a waiting posture. Heavy neutron stars have been weighed. Their existence strains, but does not yet definitively break, the cosmic evolution picture. The uncertainties are still large enough for partisans of the idea and its critics to share the same observational landscape and tell different stories about what it means. That ambiguity is not a failure of science. It is a snapshot of science in motion. Right now, we do not yet know whether these massive neutron stars are the execution order for cosmological natural selection or just a warning that the universe, like life, is more complicated than our first, neat models. The number is printed in the hearts of a few distant stars. We are still learning how to read it. Even if the numbers in neutron stars end up smiling on this idea, another, quieter question waits underneath. What, exactly, have we explained about ourselves? The promise of cosmological natural selection is seductive. On the surface, it seems to offer a way out of an awkward fork. Either the universe is fine-tuned for life by some designer, or we just got ridiculously lucky in a vast multiverse. The first option feels too heavy. The second feels too thin. The black hole story stands between them and says, maybe there is a third way. Maybe the constants look the way they do because universes that happen to make many black holes reproduce more, and we are one twig on that ever-branching tree. In that telling, fine-tuning stops looking like a miracle and starts looking like adaptation. Our universe is not a one-off lottery winner. It is a member of a large population biased towards certain properties. The masses of particles, the strengths of forces, the value of dark energy, all leaned over time toward a local optimum for black hole production. We simply woke up in one of the universes that sits on that hilltop. It is an elegant picture. But then you notice something. Even if universes evolve this way, the connection to life is still, at least partly, a coincidence. The key assumption is that the same physics that makes a universe good at producing black holes also makes it friendly to complex chemistry. In our case, that seems to be true. The conditions that help molecular clouds cool and fragment into stars also involve the very elements life uses: carbon, oxygen, nitrogen, metals in astrophysical language. The same dusty, molecule-rich clouds that will eventually give rise to black hole forming massive stars also give rise to habitable planetary systems. But that parallel could have been different. Imagine a slightly altered world where other elements, say beryllium and boron, happen to carry most of the burden of cooling star-forming clouds. Maybe, in that universe, the atomic transitions that make those elements efficient interstellar radiators do not translate into versatile chemistry in liquid solvents. Perhaps carbon chains are unstable there, or water is scarce, or the temperature ranges where clouds cool well are hostile to any known biochemical process. In that hypothetical cosmos, the best way to make black holes would be to enrich space with elements that are useless for building life. Universes that evolve toward maximum black hole production would fill themselves with beryllium and boron, dust and molecules tuned for cooling, but not for metabolism or information-bearing polymers. They would be black hole factories indifferent to biology. If that were the case, where would observers arise, if they arise at all? Only in those rare universes where, by chance, the same constants that maximize black holes also allow some subset of elements and reactions to support life. Not because life is driving the evolution, but because evolution has happened to land on a hilltop that serves both goals. A fortunate overlap between two independent patterns. From the inside, in such a universe, beings like us would look around and say, of all the branches in the cosmic evolutionary tree, of course we find ourselves on one where the constants that make black holes also make life possible. Nowhere else would there be anyone to make that observation. That sentence should sound familiar. It is just the anthropic principle in different clothes. We are back to saying, in essence, we are in a special part of the multiverse, because only in those parts can observers exist. The black hole story has added a layer underneath, explaining why certain constant values are common in the larger population of universes. But it has not removed the selection effect. It has simply shifted the question of why us up a level. To be fair, the theory does gain something. In a pure multiverse plus anthropic picture, life-friendly constants might be very rare. The explanation for why we see them is simply that someone has to. In the cosmological natural selection picture, life-friendly constants might be common, because they are tied to black hole production. The multiverse is no longer a huge lottery where only a handful of universes can host observers. It might be full of them. That matters. It changes the shape of the background story. It suggests that we are not perched on a uniquely fragile platform, but standing on a type of ground that reality tends to produce and reproduce. Still, at the local level, the feeling of contingency does not fully go away. Even in a universe tuned for black holes, there is no guarantee that life will emerge. The theory does not tell you how often chemistry stumbles into biology, or biology into minds that wonder about quarks. A human analogy helps. Suppose you are born in a city with a thriving job market. There are many companies, many roles, many paths to employment. Someone who studies economic geography might explain that cities like this are common in certain countries, that transportation networks and industries tend to cluster in specific ways. They might even have a theory about how such cities evolve and reproduce their own conditions. All of that would help explain why there are many jobs available. It would not explain why you, in particular, became a writer instead of a musician, or decided to work in one neighborhood instead of another. The macro story sets broad conditions. The micro choices, chances, and accidents that lead to your specific life are still contingent. Likewise, a universe optimized for black hole production sets broad conditions. Lots of long-lived stars, heavy elements, dust, stable structures. Within that canvas, how often life arises, how often intelligence evolves. Whether any given galaxy hosts observers may depend on chains of events that the cosmological evolution picture does not touch. It tells you why you might expect many life-friendly universes. It does not fix what happens inside each one. Even the physicist who originally pushed cosmological natural selection has voiced this kind of concern. After exploring the idea in detail, he noted that it might not, in the end, reduce the amount of luck required to explain our existence as much as he had hoped. It relocates the luck. Instead of saying, we got lucky that our universe has the right constants, you say, we got lucky that we live in a branch where the constants that are good for reproduction also happen to be good for life, and that within that branch, life actually emerged. That may sound like a small shift. Conceptually, though, it is important. It keeps us from pretending that any theory can completely remove contingency from the story. No matter how elegant the mechanism, there will always be a sense in which things could have turned out differently, and we would not be here to notice. For some, that is an unsatisfactory outcome. There is a deep human desire for a narrative that says, implicitly or explicitly, you were meant to be here. Multiverse stories of any kind, whether they involve eternal inflation, cosmic reproduction through black holes, or something else, tend instead to say, you happen to be here. The difference between those two sentences is emotional, not empirical. Physics can only ever address the second. Maybe that is the real existential undercurrent running through all of this. We keep hoping that a sufficiently clever theory will dissolve our sense of precariousness, that it will turn "we might not have been" into "we had to be." Yet, every time we add more structure to the explanation, some residue of contingency remains. Whether the universe came from a single quantum event, a branching multiverse highway, or a long process of cosmic evolution, there is no story that fully erases the feeling that things could have gone another way. A theory does not have to save us from that feeling to be valuable. It does not have to guarantee our existence or provide cosmic reassurance. Sometimes its role is humbler and, in a way, more honest. It redraws the map of where we think the mystery lives. Cosmological natural selection, if it survives its tests, would move the mystery from "why these constants, once and for all," to "why this larger process? And why does it have this particular structure?" If it fails, the attempt will still have shown us how to connect questions about the deepest laws of nature to observable quantities like neutron star masses and star formation. In either case, the contingency of our own lives remains. We are here, briefly, in one corner of one universe, telling stories about why universes exist at all. If contingency is something we can never quite escape, then part of the work of science is learning how to live honestly with that fact and still keep asking sharper questions. There is a disarming truth here that the originator of cosmological natural selection has been open about, and many of his colleagues quietly agree with. If you press them in a hallway, late at night after a seminar, a lot of physicists would probably say, "This story about universes evolving through black holes is, more likely than not, wrong." And yet, they keep talking about it. That might sound strange from the outside. Why spend time on an idea that is probably not true? But this is how physics has always moved at its edges. The history of the field is full of beautiful, carefully built theories that were later set aside as literal descriptions of nature, but not discarded as mistakes. They did important work on the way out. Take the ether. In the 19th century, many physicists thought light must be a wave in some medium that filled all of space. That medium was given a name: the luminiferous ether. People tried to measure the Earth's motion through it. They designed experiments to see how light speeds differed with direction. Those experiments came back with a stubborn result. No sign of the ether wind. The idea, as a physical substance, eventually had to go. But in trying to save it, people discovered how far you could bend classical notions of space and time. The eventual replacement, special relativity, kept some of the mathematical bones that had been developed to describe an ether and reinterpreted them. The old idea failed as a picture of what is out there. It succeeded as scaffolding for what came next. Early models of the atom tell a similar story. There was the plum pudding picture, with electrons embedded in a positive goo. There was the miniature solar system picture, with electrons orbiting a nucleus like planets. Experiments showed that these images, as literal accounts, could not be right. Electrons would radiate away energy and spiral in. Scattering experiments revealed a compact, heavy nucleus. Quantum mechanics eventually took over and replaced orbits with orbitals, waves, instead of little balls. Yet the wrong pictures were stepping stones. They framed questions. They guided experiments. They forced physicists to clarify what they meant by stability and radiation. They made the holes in existing ideas visible. At the frontier where cosmology, quantum gravity, and the multiverse live, we are in a similar zone. Hard data are scarce. We cannot build another universe in a lab. We cannot peer past the horizon of a black hole. We have the cosmic microwave background, large-scale structure, gravitational wave signals, the statistics of galaxies and stars. Those are precious, but they do not reach all the way down to the level where, say, a bounce inside a black hole might seed a new region of space-time. In such a landscape, progress often starts with bold proposals that reach beyond what we can currently test. Ideas that sketch possible structures of reality, knowing full well that most of them will die. The crucial thing is what happens next. Do they sit there, forever out of reach? flexible enough to survive any future observation? Or do they claw their way back toward testability, tying their assumptions to things we can, eventually, measure? The virtue of cosmological natural selection is that it has genuinely tried to do the latter. It does not just say, universes reproduce somehow, therefore we exist. It says, if universes reproduce through black holes, and if constants mutate slightly, then certain patterns should appear. It sticks out specific claims. The maximum mass of neutron stars should sit near a particular value. Small changes in constants from our observed ones should generally decrease the number of black holes, not increase it. Universes that look very unlike ours in their dark energy content should, under certain assumptions, be poor at making the kind of black holes that count. Those are structural statements about how reality might be organized. They can be challenged by observation and by rival calculations. They are not infinitely malleable. You cannot easily adjust them to accommodate any possible universe you might imagine. Compare that to unfalsifiable stories that can explain everything with equal ease. There are versions of multiverse thinking, for example, where any observed value of any constant is simply declared to be the outcome of some selection effect, with no further constraints. There are metaphysical pictures in which every logically possible universe exists somewhere, and we are guaranteed to find ourselves in one compatible with our memories. These ideas may have philosophical interest, but as physics they are hard to kill, and therefore hard to learn from. If your theory can account for any universe with any constants and any history, it might, in a practical sense, explain nothing. It becomes a background assumption, not a tool for understanding why this universe looks the way it does. One way to think about the difference is in terms of questions. Science does not move only by answering old questions more precisely. It also moves by inventing new questions that did not exist before, and then building the tools to approach them. Does our universe reproduce? Is one of those questions. Nobody in the early 20th century would have known how to even pass it. The combination of general relativity, black hole physics, quantum theory, and cosmology had to mature before the question could be asked in a serious way. Once you ask it, other questions line up behind it. If it does, how? Through what mechanisms? With what inheritance? What counts as a descendant? How would that change what we expect to see? Speculative ideas like cosmological natural selection are ways of walking around in the vast space of logically possible realities and marking out paths. You know, from the outset, that most of those paths will not correspond to the world we live in. That is not a flaw. It is the whole point. Somewhere in that space, there is at least one path that matches our universe. The job of theory is to find it, or at least to rule out many others. In practice, this does not feel grand. It looks like workshops in mountain resorts, where people crowd into small rooms after dinner and argue at the board about whether baby universes violate conservation laws. It looks like email threads where someone points out a loophole in a proposed test. It looks like observational astronomers rolling their eyes and saying kindly, "If you want us to care, tell us what to measure." There is a human texture to it. People get attached to ideas. They also learn to hold them lightly. One speaker might end a talk by saying, with a small smile, that he gives his own theory a low chance of being literally true, but a high chance of being useful. Useful, in this sense, means that it organizes existing knowledge in a new way, spurs new calculations, and suggests new observations, even if it eventually gives way to a better framework. It is important to keep hope and belief separate here. Cosmological natural selection is not something to cling to because it is poetic, or because it gives black holes a dramatic new role. The aim is not to find a story that makes us feel more comfortable. The aim is to let this be one candidate among many in the ongoing conversation about why reality looks as it does. If future measurements of neutron stars, or better understanding of dark energy, or a more complete theory of quantum gravity, all line up against it, then the right response is to let it go, not with cynicism, but with the quiet satisfaction that comes from having learned something in the process. We will know that certain ways of stitching together black holes and multiverses do not match our world. That negative knowledge is still knowledge. If, on the other hand, parts of it survive, perhaps in altered form if black hole bounces turn out to be real in some models of quantum gravity, or if our universe does, in a clear sense, sit near a maximum of black hole production for its dominant channel, that too will be information. The story may be reshaped. The reproductive metaphor may be softened. The details will certainly change. Either way, the question it raises will still have done its work. It will have made us think more carefully about what we mean by a universe, about what counts as an explanation, about how local our intuitions about design and evolution really are. From your vantage point as a listener, lying in the dark with headphones on, none of this changes your immediate life. Tomorrow, you will still wake up in the same world, with the same worries and small joys. Black holes will keep pulling on nearby stars, regardless of how we talk about them. If universes reproduce, they will continue doing so without asking our permission. But there is a quiet gift in understanding why a story like this was told, and how it might fail. Even if cosmological natural selection turns out to be wrong, the effort to test it will leave us with a clearer sense of what a universe must be like to give birth to ours. It will sharpen our sense of which features of our world are contingent and which are structural. It will remind us that, at the edge of knowledge, science breathes through speculative ideas that dare to be precise enough to die. If speculative ideas are the way science breathes, then what we do with them afterwards is the way we learn to breathe inside our own lives. So take everything we have walked through and compress it, just for a moment, into a single, slow breath. A universe whose basic numbers seem suspiciously well placed for stars and chemistry. Black holes that are not just heavy objects, but possible gateways where known physics falls silent. A proposal that universes might reproduce through those gateways, with their constants drifting the way genes mutate, drifting towards settings that make more black holes. Tests hidden in the maximum mass of neutron stars and in the structure of dense matter. Cracks where other possibilities intrude. Vacuum black holes, different ecologies of universes, the anthropic principle slipping back in. All of that brought us to a question that is less about equations and more about posture. How do we stand in a universe that might itself be one event in a larger story? Or that might not? For the sake of clarity, imagine reality branching in two conceptual directions. In the first branch, the bold idea is right in its essence. Black holes really do give birth to new universes. The singularity is cured by quantum gravity into a bounce. A new region of space-time opens up on the far side, expanding, cooling, writing its own history. The child universe inherits its laws, with slight changes, from the parent. Over an unthinkable expanse of meta-time, a whole family tree of universes grows. In this branch, our cosmos is not unique. It is one generation in a line that may stretch back through countless bounces and forward into countless descendants. We will never see that tree directly. The horizons between universes keep them causally sealed. But conceptually, the picture is clear. Our universe is not the whole of reality. It is a local bloom on a much larger organism. There is a loss here. We are no longer living in the only universe, at the center of anything. But that loss is familiar. We have been through it before. When people realized that Earth goes around the sun and not the other way, something similar happened. We were displaced from the center. And yet our sense of belonging deepened. The solar system became a neighborhood. The galaxy, a city. The cosmos, a continent we had only just begun to map. If black holes make universes, a similar shift plays out at another level. Our cosmos becomes one neighborhood in a supercosmic landscape. Our laws are not handed down once and for all. They are one local dialect in a language that might have many accents. We are not the purpose of the universe. We are a local maximum of awareness in a larger process that, without any intention, has become very good at generating complexity. Meaning, in such a picture, is not erased. It is decentered. The fact that universes evolve to make black holes tells you little about whether kindness matters, or whether art is worth making, or whether you should call someone back when they are lonely. Those questions live at a scale where cosmic reproduction is background noise. Yet your sense of context changes. You are part of a species that has emerged in a universe that is itself part of something like an ecosystem. In the second branch, black holes do not make universes. Gravitational collapse ends in some other way. Perhaps quantum gravity removes singularities without producing new, causally disconnected regions. Perhaps there is only one Big Bang in the larger reality, and our constants are fixed by a deep mathematical structure, or by a single quantum event, or by something we do not yet have language for. In that branch, the fine-tuning of the constants remains, but is not smoothed out by cosmic evolution. There may still be a multiverse of some other kind, perhaps from eternal inflation, perhaps from a landscape of vacuum states. Or there may not. Either way, the particular combination of numbers that makes our universe hospitable to life stands out as one possibility among many. Selected not by reproduction but by whatever rule set underlies everything. The contingency of our existence feels even starker there. The gap between what is and what could have been is not filled in by generations of universes drifting towards certain attractors. It stays open. Perhaps there is a single deep theory that says, in effect, there was no choice. These constants had to be as they are. Perhaps there is not, and the values are just the way a particular cosmic throw of the quantum dice landed. In both branches, the universe remains vast, and we remain small. In both, we are fragile organisms piecing together a story about why there is something rather than nothing, why the something follows certain patterns, and why those patterns, accidentally or not, include us. The speculative structure you adopt above that does not change the fact that you have a finite number of mornings, a limited number of conversations, a life that will end long before any neutron star spins down. So zoom the scale back down. Imagine someone standing tonight under a city sky. The streetlights are bright. Neon signs wash the buildings in color. Above, the sky is not a deep black, but a washed-out orange or gray. Only a handful of stars are visible. Maybe a bright planet, maybe the moon if it is up. Most of the cosmos is hidden behind the atmosphere and the glow of human life. That person may not know the details of quantum gravity or have opinions about strange quarks. But if they have followed this journey, they know that in the hearts of some of the stars they cannot see, light is burning in a way that will end in collapse. They know that, in dense clusters and galactic centers, black holes are already there, curving space-time so strongly that not even light can escape. They know that somewhere inside our theories, and inside our ignorance, there is a live question about whether those collapses echo into new universes, or simply mark the edge of ours. They also know that tomorrow morning they will have to wake up, go to work, answer messages, make decisions that have nothing to do with event horizons. The grandeur of these ideas does not get them out of a single human obligation. It might, if anything, make those obligations feel more precious. It is tempting, at the end of a story like this, to tidy things up, to deliver a verdict, to say, softly, that one branch is more likely, or that the evidence points firmly in one direction. But that would be dishonest. We do not yet have a working theory of quantum gravity. Our understanding of dense nuclear matter in neutron stars is incomplete. The nature of dark energy is still a riddle with numbers attached. On these points, the universe is not yet speaking clearly to us. So instead of answers, you get something different. The responsibility to decide what these possibilities do to you. You have now heard the case for and against the idea that black holes might be parents of new universes. You have seen how the notion arises from real physics, where it leans on speculation, where it reaches toward testable predictions, and where those predictions are under pressure. You have seen how, even if the idea fails, the questions it poses are not wasted. So now the question is yours. When you imagine a black hole, do you picture a pure ending, a place where information goes in and never comes out, a period at the end of a cosmic sentence? Or can you, at least in the corner of your mind reserved for maybe, also see it as a possible doorway. A place where this universe narrows to a throat and something else, forever beyond our view, begins. There is no right answer. There is only the way you carry the question. However you carry it, one fact remains. Quietly astonishing. Whether or not black holes create new universes, this universe has already created something remarkable. Out of hydrogen and helium, out of stars and heavy elements, out of chemistry and cells and nervous systems, it has produced at least one species that can stand under a polluted sky and wonder, honestly, if reality itself can have children. That, on its own, is a kind of miracle that does not require design or destiny. It is simply what happened here. In one small corner of one possible universe, curiosity learned to ask whether the darkness between the stars is only an emptiness, or also a cradle.